Here is a question that looks almost too simple. I will give you a handful of ranges, 1 to 4, 2 to 5, and 3 to 6. And all I want to know is which single number is covered by the most of them. With 3 ranges, you can eyeball it. But imagine a million ranges within points anywhere from 0 to a billion. Suddenly, the obvious approach, walking through every number inside every range and tallying, is hopelessly slow. There is a beautiful tool that does this in essentially one pass. Most people memorize it as a magic little formula without ever understanding why it works. So the moment a problem is shaped a little differently, they are stuck. We are going to do the opposite. We will start from that slow, obvious solution, feel exactly where it wastes effort, and let that push us to invent the fast one ourselves. We will even get a key step wrong on purpose, watch it break, and fix it. By the end, you will not just know the trick, you will recognize the whole family of problems it solves. Let's nail down the exact answer by hand first, so we know what we are aiming for. Each range covers every whole number between its endpoints, both ends included. 1 sits inside only the first range, so its coverage is 1. 2 is inside the first and the second, so 2. 3 is inside all 3 ranges, so 3. 4 is also 3. Then 5 drops to 2 and 6 to 1. So the most covered number is 3, with a coverage of 3, easy by hand. The real question is how a computer does this fast, not for 3 ranges, but for millions. The most natural idea is the direct one. Keep a count for every number, starting at 0. Then take each range and walk across every number inside it, adding 1 to that number's count. Let's watch it. We reset to 0 and rebuild the counts the slow way. The first range bumps these 4 counts, one at a time. Notice that was 4 separate additions for just 1 range. The second range bumps 5 of these, and the third bumps these. It is completely correct, but watch what it is doing. A single range update was smeared across many consecutive cells, one at a time. That is the first clue. When you repeat the same simple operation across a whole block, again and again, there is wasted work, and waste usually means a better structure is hiding. So before we even know the solution, let's name the smell, because recognizing it is more valuable than any single trick. Feel this alarm whenever a problem looks like one of these, adding the same value to every element in a range, updating an entire interval, or counting how many intervals cover each point, which is exactly our problem. The moment you see any of these, one question should fire in your head. Can I get away with recording something only at the boundaries, instead of touching everything in between? Everything that follows is the answer to it. To answer it, let's shrink the problem to a single range, 2 to 5, and stare at it until it gives up its secret. What does this one range contribute to each position? At 0 and 1, nothing. At 2, it contributes 1. At 3, still 1. 4, 1, 5, 1. And at 6, back to 0. Now read it like a story. It turns on at 2, stays flat across the whole middle, and turns off just after 5. Everywhere in between, each value just copies its neighbor. All the real information in this range is 2 events, not 6 values. That realization is the whole idea, so let's act on it. Instead of storing the values, store only the changes. Put a +1 where the contribution starts, at position 2, and a -1 where it stops, at position 6. This array of changes is the difference array. Now sweep left to right, carrying a running total, and at each position add whatever change sits there. Watch it rebuild the exact contribution from just 2 marks. That running total is the prefix sum. Now the part everyone memorizes and nobody questions. Why -1 at 6 when the range ends at 5? Let's get it wrong on purpose. Put the -1 right at the end, at 5. Sweep again and watch. At 2, 1, 3, 1, 4, 1. And then at 5 we subtract immediately, so the total drops to 0 right here. But that is wrong. 5 is supposed to be covered, and we just erased it. The subtraction fired 1 step too early. The range includes 5, so coverage should only fall off at the very next position. So push the -1 1 step right to 6, which is R+1. Sweep again, and now 2, 3, 4, and 5 all hold at 1. That is the entire reason for R+1. You never memorize it, you rederive it in 5 seconds by watching 5 fall out. There is a second way to see this that many people find even more intuitive. Throw away the array and think in terms of events. Read every +1 as an interval starts here and every -1 as an interval ends here. The starts are at 1, 2, and 3. The ends are just after each range at 5, 6, and 7. Now walk left to right, holding one counter for how many intervals are active. At 1, 1 active. At 2, 2. At 3, 3. Still 3 at 4. Then 2, then 1. The active count at each position is exactly how many ranges cover it. Same answer, no array to reconstruct. The original question now answers itself. Just remember the highest point the active count reached. It peaks at 3 with 3 intervals. On cost, if the numbers are small, use a plain array and it is order n plus the range, basically linear. If the coordinates are huge, do not allocate a giant array. Sort the 2n events and sweep, which is order n log n. Pocket 3 recognizable shapes. 1. Add some value x to every element from L to R. Difference array, plus x at L, minus x at R plus 1. 2. How many intervals cover each point or where the maximum overlap is. Start and end events, plus 1 at L, minus 1 at R plus 1, then prefix sum. 3. Many range updates, then one final read of the array. Difference array again. If a problem smells like any of these, you already know the tool. Let's retrace the path, because the path matters more than the destination. Brute force wasted work on every element. That waste was the clue. We stored only the boundaries, +1 and -1. A prefix sum rebuilt the counts. We derived R+1 by watching the bug, and we reframed it as a sweep line of events. And underneath every step is a single idea, the one thing worth carrying out of this video. If a quantity stays constant over a long stretch, do not store the quantity. Store only where it changes and rebuild the rest with a prefix sum. Store the changes, not the values. Master that one sentence, and a whole category of problems stops being tricks you memorize and becomes something you can simply see. Thanks for watching.